values, so they would be at the same usable capacity. And so that's where you're seeing, once that's added in, this significant reduction when comparing these two systems side by side. Costs are coming down about 10% from 2020 to 2021. But if you're like me, you'd say, well, that's hard to know if that was a really good representative year, because a lot of things were different in 2020. But even a more recent report, we do continue to see this sharp decrease in energy storage costs. So this was based on a baseline of 2020. So you see here 2022 data. In 2022, we see to when this came out in 2023 and projecting forward, we see a substantial decrease to the point where by 2025, we're projecting that we'll have had a 20% decrease in the capital costs of 4-hour battery energy storage. And then if we look ahead to 2030, only about 5 to 6 years ahead, we're talking about a 30% decrease in the cost. So almost every year of this project, I've had to ask my students to go back and update the costs again, because it's changing some of the conclusions. Something that didn't really seem feasible a few years ago is all of a sudden looking more and more feasible as the costs change. Okay, so something to keep in mind, one of the reasons why it's being talked about. So is the 2024 just a glitch and just kind of a hiccup in the data? No, it's pretty steady and significant increase in battery energy storage capacity going on throughout the United States. You can kind of see where we've been. You can see what the projections are, and I suspect we are only at the beginning of this. So battery energy storage is increasing. What is it being used for? Well, there's a lot of usage, and if you'd asked me that question a couple of years ago, the answer would have been frequency regulation. Frequency regulation was always the dominant thing with energy storage. But all of a sudden, the number one now is arbitrage. Arbitrage is the ability to try to leverage energy use and pricing for the times that you want it versus times that you don't. And all of a sudden, that has really seen a big uptick since about 2019. And 2019 and before, frequency regulation was pretty much everything. And then you had these other little usage of energy storage. But they were all minor in comparison. Then since then, arbitrage has been on a steady increase, okay, where we're seeing more and more capacity being installed for batteries for this use case. And so what is energy arbitrage with batteries, and how exactly do we take advantage of it, and how does it benefit clients? That's one of the things we'll be talking about, and then the extension of that to reducing carbon emissions is what we're going after today. So a little bit of background just to make sure that we all understand why this discussion is happening. It's probably doesn't surprise any of us that cost of electricity varies, right? We're probably all used to that. We're used to probably seeing a graph kind of like the following. In many states, we see that pricing for electricity is usually higher in the afternoon. Often when we're hitting maximum air conditioning load, especially here in Arizona. So you see between about 3 and 8 p.m., we jump from about a little less than 6 cents per kilowatt hour to almost a little bit over 7 cents, okay? And that's just one example of really typical pricing for electricity. However, while that's common, things are becoming a lot more dynamic, and utility companies are talking about how things are changing, because what you've seen in the past isn't necessarily what we're going to be seeing going forward. Why is this happening? Well, I don't probably need to say too much about the California duck curve. We're probably all pretty familiar with that. We see, of course, this results in really high penetration of solar, results in really low electricity costs in the middle of the day. It's this ramp that's so concerning. That's what has electricity costs, really jumping up towards the end of the day. And we'll see on how we can kind of leverage that with a battery energy storage system here. This is an example of some recent data pulled from California for their wholesale electricity prices. And you can see it really, again, resembles what's happening with the duck curve, that we have this low energy pricing down to 4 cents. And some reports I've read, they're expecting that to get even cheaper, right? So, and you can kind of see the changes from 2021 to 2023, where we have this gradual reduction in the middle of the day in price, followed by an actual increase at the end of the day, where we're approaching that 6 to 10 p.m. range. That cost of electricity just keeps going up. And that's the general expectation in conversations I've had, is that where we used to see peak pricing around 3 to 6 p.m. It was kind of typical. We're now expecting peak pricing to shift, and especially here in Arizona, to later and later hours, as late as 10 p.m. and potentially beyond, which again is all related to some of these changes that we're seeing. So big changes happening due to renewable penetration, and all of a sudden things that maybe weren't as possible in the past are becoming real opportunities, and that's where battery energy storage is coming in with this energy price arbitrage. You can see here, if you just note that difference, 4 cents to 13 cents, that's more than a factor of 3 change, okay? So that's what we can take advantage of with a battery. How do batteries do it? Well, we've referred to these programs as some sort of a demand response program. This one, if we just are talking about kind of this load shifting situation, we sometimes refer to that as price arbitrage, okay? It's the fact that the prices differ, and so we try to buy electricity when it's cheap, and then we try to give back or use our storage when it's more expensive. So for example, we can discharge, in this particular client's case, in the afternoon. We've already shown that generally we have highest pricing here in the afternoon hours, and that's differs by location, but true in many places. And so we're avoiding this particular client, for whatever reason, they can't potentially shift this. They need to have this really high energy use at the end of the day. Well, the best thing for them to do is to just discharge it. Okay, we call that peak clipping, trying to reduce that demand on the grid and ultimately save them money in the process. Right? The other thing that you then have to do is you have to charge that battery at some point, right? And you're ideally going to charge it when it's cheap. And so we've already kind of seen late evening hours and increasingly later and later evening, really coming to more early morning and even middle of the day is becoming the time to charge because of the differences in the time of use pricing. So we call that valley filling when we start to bring our lowest electricity use up. And ultimately that accomplishes something we call load shifting, right? We're trying to redistribute that load. This is a benefit for the customer, the client, whoever they may be, right? They want to have ultimately lower cost electricity. So by shifting, they achieve that. And it's a benefit for the utilities. The utilities don't really want to deal with these huge peaks that cause them to have to change their generation strategies and kick on potentially these diesel gensets that are much more inefficient and others that have to deal with the large ramps. So we call that price arbitrage. We're trying to charge when it's cheap, okay, discharge when its prices are high. That's part of a bigger effort called demand response, and I'll get into that a little bit, but demand response is really a big change, and we're seeing it talked about more and more, where we want, instead of having the historical case where consumption directs generation, to demand response is when the utilities try to direct the consumption by putting in price triggers. Time of use pricing is just one example of demand response. So if arbitrage is working, which we've kind of seen from the graph, that's the majority of the installations, and I've shown you some of the reasons why and why the situation's changing. We might ask, can we do this with carbon emissions? It turns out that carbon emissions are not constant on the grid, and that probably doesn't surprise anyone. Usually our base load is usually nuclear energy in many states. That's the case in Arizona. It's one of our big base load power generation sources. And usually as you try to get to those times when you've got peak generation needs in the afternoon and the evening hours, that's when we're starting to hit the things that are most inefficient, usually have the largest carbon emissions. And so as a result, you see a graph kind of like the one you're showing here, where we have marginal emission factors for, in this case, carbon, and they're varying over the year. We see they're highest in the summer months, and that's the case here in Arizona. We typically hit our peak load sometime in July and August. Okay? And it'll vary where you are, but as a result of when you're hitting your peak, that's typically how your carbon emissions will typically follow those general patterns, just based on where that generation comes from. Okay. So instead of just thinking about price arbitrage and trying to get capital benefit, can we actually move these carbon emissions? For example, can we charge our battery when the carbon emissions from the grid are really low? And then can we discharge the battery when the carbon emissions are in the grid are high? And then by that, actually save scope 2 emissions for particular clients and facilities. That's one of the questions I'll answer towards the end. I've got a lot of background to give and setup to do to kind of help you understand how these systems work, but that's ultimately where we're headed and what we'll talk a little bit about. So let me just give you a quick overview of some of the literature and what the things that are happening in this field and the methodology we use to be able to approach this problem. So battery energy storage is really common, being investigated a lot from a price arbitrage standpoint, from a peak clipping standpoint, and others. We've looked at a number of papers just to try to understand who's working in the space and what are they studying. As you can see, residential, a number of studies in that space. Most of them recommend storage of, really small energy capacities on the order of 10 kilowatt hours of energy storage, and they have smaller annual revenues as you'd expect. Whereas commercial buildings tend to have a much larger range, right? We a lot greater size differences in commercial buildings. You typically talk about small commercial and large commercial. Well, you see some of that playing out with the differences in the energy storage sizing that are ideal. So these are other papers that have tried to optimize energy storage for various clients. We see microgrids where typically in a microgrid you can maximize your annual revenue because you're typically fully off grid. So we see high annual revenues, range of energy storage capacities, some distribution applications, some industrial applications, although we haven't found quite as many of those studies, and that's an area where our group works quite a bit, and we've been working with the local utility on. So you can kind of see we've done some recent work to try to understand what are typical sizes for industrial clients and how do they compare. Okay, so there's some work in this space, different people looking at optimization. I will note that a lot of the studies, and you can see here, the same exact studies, but a lot of these are actually hybrid systems that they're talking about. They're not battery only. We're talking about a renewable plus a battery storage system, the annual revenues and capacities from that. We're going to strictly limit ourselves today to energy storage only, okay? Much less studies in that space, but very interesting trends and results, which we'll show you when we start to think about battery as a standalone system for generation. So now, what do we need to do to actually size these systems? Well, one thing we need from clients is real data. Okay, a number of these studies, they don't always have a whole lot of data from clients, and so that is kind of a limitation because the reality is clients' electricity use varies significantly. You can see this is what we call 15-minute interval data, and we see significant variations throughout the day in terms of the electricity use. We can see if you go day to day, we see a lot more fluctuations. These have been looked at for the entire week. We see kind of the general trends. We can basically see that they're shutting down on Friday. Looks like they kind of power down on Monday. They're starting back on Tuesday and Saturday. So we can already kind of tell that this facility has different usage patterns. They're shutting down on the weekends and maybe on starting up on Sunday again and then closing down on Monday night. So they have different maintenance schedules potentially. We can average out that data, get general trends. It's all helpful, but really the average is not as important as the actual usage scenarios because when we're talking about arbitrage, it's talking about what's happening in the little gaps. That's what we need to know in order to assess feasibility. So one of the things that we've done in our modeling is we've made it so we can utilize 15-minute data to make sure we're getting really accurate predictions based on real clients' data. The other thing we've noted is that you look at one client and you assess energy storage, that's great, but one client is one client, and that doesn't start to give you the bigger picture that we're trying to get with this study of how we think about energy storage from a much, much bigger perspective and across a lot more clients. So we'll get to some of that at the end. But just two examples here. These are two industrial facilities. The one on the left, we'd consider that something of an intermittent process. So notice they basically have really low energy use in the mornings. Then we get really high energy use from about 3 a.m. to about noon. Then they're kind of shutting down, not as much energy use in the evenings, right? And then we see that they don't really operate too much on the weekends. It's mostly a Monday to Thursday operation. We can gain a lot just by looking at this graph. This is kind of an example of what you might see in a bakery, for example, typically starting very early, preparing their product, and then often a lot of that energy use is gone by the end of the day. Whereas this other facility, kind of running continuously, we do see a little bit of a drop here between 3 a.m. and 9 a.m., but much, much more consistent throughout the day, kind of a continuous process facility. And this might be more common for what you might see in like a wastewater treatment plant, for example. So two very different facilities, and they're going to have very different answers in terms of the applicability of energy storage and their ability to leverage energy price arbitrage and carbon emission reductions. So how do we attack this? Well, first we need a model to do it. And we've got the data from real clients, but we need a model to tell us how would a battery system look for this client if we consider all the relevant factors for that battery system. So the first thing we want to consider is the capacity. We need to say, well, we're going to model many, many different energy storage capacities, and we're going to look at a range. Once we fix the capacity, we typically also fix a depth of discharge. We don't typically take a battery all the way down to zero, or if we do, it's very rare we ever get that close. So we often talk about trying to stay above 20% of the capacity. Okay, so you can kind of see that kind of limits our general range that we're operating in. We can't charge these things infinitely fast. They are limited, right? So we have, for example, a maximum charge rate. We need to make sure that we stay always below that. So we build that in as a constraint. We have similarly a maximum discharge rate. We talk about the number of C's of the battery, right? Those are what those are related to. So now we have to fix that. We can't be anything less than that line. Okay? And then ultimately we might want to charge and discharge at certain times. We want to have time of use pricing built in. All of those factors to consider so that our battery system's trying to optimize around all of them to really tell us best case scenario what can happen. Okay. We can look at different energy storage types. Today I'm really going to talk about lithium ion as one of the big ones that's being applied in this space, but we can, the answers change a little bit depending on the technology because they have different charge rates, capacities, costs, etc. But that's generally what the model's doing. It has all these factors built in that it's considering. And then the last thing that we did is we built in the economics of it. And you'll see here that we did a couple modifications compared to what's typically done in the literature. One is that many people consider capital costs to be essentially zero when you have nothing installed. And while that's true, we know that if you install anything, there is a little bit of engineering, procurement, construction costs that it isn't cost $1, right, for a really, really small system. There's a little bit of a difference there. And so we build that in, okay, to our model so we can account for the fact that when you get really small, it doesn't just become really, really cheap. There actually is some costs that are still kind of always there. And then we start to build out our cost savings. Okay, so this first term evaluates cost savings. We built into it some potential for the utility costs to change, and we'll see how that affects the system. We built into it operation and maintenance costs, okay, and we also built in it the ability for those costs to change over time, which they can. We look at the capital costs, and now we also have that engineering, procurement, and construction costs built in as well. So some very slight modifications from our model compared to others, but in general, we're attacking a lot of the same rough concepts and trying to assess energy storage feasibility. So some results, again, preliminary, but there's a lot I'll have to share with you today. So the first is kind of understanding how our objective function works. This is what we're trying to maximize is our savings here. Okay, and how does this actually affect a battery system? So let me walk you through this. This is the first one. We're going to look at several of these today. You'll notice that this green line is our inventory of our batteries. So way down here, this means battery inventory is really low. We're charging up to a maximum of about 2,000 kilowatt hours. This is basically fully charged battery. We're going to have some discharge here and go back down to about that, depth of discharge we want to hit. At the same time, we've got our time of use pricing. You can see we're hitting our maximum between about 3 p.m., 6 p.m. range, as we talked about. And then we call this shoulder pricing, not quite as high as the peak pricing, but kind of in the transition range. And then this is our low cost electricity. Notice what's happening here with our model. This has been optimized for this particular client. See, on this particular day, we come in, our battery storage is pretty much completely uncharged. We're then going to charge it, okay, when the time of use pricing is low. We're going to then hit a point where we don't want to charge anymore. We've come up in our pricings. We're getting that shoulder pricing now, and so we don't really want to charge there. That's not the optimal time to charge. We then hit our highest cost electricity when we start to discharge. So notice what happens. If we just look at usage savings, right here in this charging range, we're actually having an increase in our energy of the facility, right? We're buying more than we were otherwise expected to. So that's an additional cost to us. But then we're going to start to discharge it here when the time of use pricing is high, and we're going to save money by doing so. But what's interesting is we don't actually fully discharge. We kind of get to a point where high cost, and then we keep it constant. Why is that? Well, you'll notice the reason is the demand savings. Right here is the peak demand, not only for this client, but potentially for the entire month, usually. And so if we want to not only leverage the high cost electricity and trying to reduce that cost, we also want to bring down our entire demand, because facilities are demand based on when they hit their peak for the entire month. So in this case, we gather some additional demand savings by discharging. Even though the utility cost isn't quite as high, we're going to actually get more demand savings by discharging right now in the day. The last piece we've got to add into this is what's called the cost of discharge. Okay, how much does it actually cost us to discharge a battery every time? How do we pay for it? Well, there's two ways to think about that. When we first started, we thought about breaking up the cost of discharge in terms of the entire capital cost that a battery has over its entire life, and the energy use of that entire battery over its entire lifetime, and basically breaking out that capital cost into every single time it discharges. So our first model, we modeled it with this modified factor here, which tells us a lot about how we can break it up over the entire time. And then we also said, well, that's kind of looking at the battery investment kind of going forward. How do we price it if we're thinking about it, in the future, and we haven't installed it yet, and we want to break up that cost. But what after we've installed it, if that cost has already been spent, well, maybe we want to think about the cost as more of the operation and maintenance costs on a regular basis. So these were the two models that we used for the cost of discharge. Okay? You can see how some of the factors that are considered in those. And ultimately, that led us to two very different results. We then lumped our first cost of discharge model into this general framework, which we call peak clipping. Okay? And you'll see in a minute that this model really works to only when the costs are sufficiently high, and typically that means that it really only targets the demand savings. It doesn't, usually the cost of discharge is higher than the usage savings, and so it actually doesn't charge and discharge very often. It's only going after peaks for a facility. Whereas our other model, load shifting, really is targeting almost every day, as long as that cost of discharge is lower than the usage savings, which it typically is, then this is going to charge and discharge on a regular basis. Let me show you what that looks like. Here's this exact same facility optimized for a peak clipping strategy and a load shifting strategy. So notice in the peak clipping strategy, the battery not doing anything, charges once, discharges once, and then doesn't do anything for basically the entire rest of the month. And you'll notice it's really just aiming for this one peak. This is the peak for the entire month. And in that strategy, we're just going to try to clip that peak and save on the demand. Alternatively, the load shifting strategy, because that O&M cost is much lower than the usage rate, it wants to take advantage of load shifting every single day. So notice we're charging and discharging every day. And even on the day of that peak event, we still trim that peak in the load shifting strategy, but we've also saved some additional money by trying to leverage that price arbitrage. Okay? So those are the two strategies, the peak clipping and load shifting. We've been working on both to try to understand what strategies make sense for clients. And ultimately, we'll show that load shifting is really the better strategy, but I wanted to set that as a baseline for our model. Okay. Now, what does it mean in terms of the actual day? Let's just take a quick look. This is that same facility, just looking at that one day where they hit its peak. Notice in the peak clipping strategy, again, we're coming in basically right at the depth of discharge we can go to. We then ultimately are going to charge, and you'll see that even in the load shifting strategy, we have kind of a similar point here. This is about the same. This charge is about the same. What's different, though, is that in the load shifting strategy, we don't just go for the peak. Notice we charged once, we discharged once with the peak, and that was it. Whereas in the load shifting, we actually charge, discharge, and then discharge again, okay, in order to try to maximize both usage and demand savings for the client. Okay? And it turns out that in the load shifting strategy, we actually get slightly more demand reduction just because of the way the model optimizes in comparison to the peak clipping strategy. So that's great. We've now demonstrated that we have two models that can ultimately show us how to shift our demand for various clients. to optimize it for load shifting or peak shaving strategies. Now, what about this demand response I talked to you about? We said that really time of use pricing is an example of demand response, but it's not the only one. There's also something called event-based demand response. In Arizona, that typically means it only occurs around 7 to 8 times per year. These are typically the 7 highest temperature days of the year. So for us, between June and August is most of our demand response events. And for us, they're typically between 2 and 3 p.m., or 2 to 3 hours in duration between 3 and 9 p.m., kind of that typical range I've been showing you where we're expecting the concerns. We now build an additional constraint into our model, which says if you've got capacity, we're going to basically force you to discharge during this demand response event because we want to maximize those savings. Why? Because those savings are actually significant. The demand response events in the western states typically around $40 per kilowatt and 9 cents per kilowatt hour. Those are big savings compared to the differences that you can achieve by just leveraging energy price arbitrage alone. And so we build that into our cost savings. And we, again, consider a lot of factors. Remember, we're taking into consideration the increase in utility costs, inflation rates, and discount rates, and then ultimately the increase in O&M rates. So all those are built in. We'll kind of show that a lot of those factors aren't very significant in terms of the profitability of this technique. So now let's add to our model event-based demand response incentives and see what happens. So I want to first show you exact same facility. And in this case, this is a day of a demand response event, okay? And the demand response event happens to occur right around here. But in this case, it's not the peak for the entire facility for the month. And so if we don't consider demand response enrollment with a peak clipping strategy, the battery says, don't do anything, right? It's not charging until the very end of the day. It looks like it's going to get ready because the next day it might hit its peak. And so it's getting ready for that event, but ultimately it just ignores the demand response event. In comparison with the load shifting strategy, again, just like we expected, charge when it's cheap, hang on during the shoulder months, and then discharge as much as you can during the high time of use pricing. But again, it actually turns out that DR event is a little bit later and it completely misses it with the load shifting strategy. So now we build in that constraint of DR enrollment, right? And all of a sudden everything changes. Peak clipping now does charge, and now we discharge during the demand response event. We're trying to maximize those savings, and notice it hangs on until the end of the day when that event actually occurs. Load shifting does something fairly similar. We're charging, okay, and a couple of times, in fact. We discharge right at the point where time of use pricing comes up. That's kind of leveraging that energy price arbitrage. And then we save it, and we end up saving that energy so that we can discharge as much as we can for the entire demand response event. In fact, if you look at the scale here, notice that we've actually put energy back on the grid, put electricity back in the grid in this case, because that was the most economical strategy, as long as the grid allows for it, to fully discharge and push some to the grid because of those significant demand response savings. So now we see that the model not only accounts for 2 different control strategies, but DR enrollment. In terms of the economics, just to give you an idea, and I've already hit on this a little bit, but just to kind of show it to you a little bit more clearly, in red here we have our total savings that have been optimized over a bunch of different energy storage capacities from 1 to 10,000 kilowatt hours. You'll see that when we do the peak clipping control strategy, almost all of the savings are demand savings. We have very little usage savings. We have also fairly low O&M. When we go to load shifting, now we start to still have, fairly significant demand savings, but our usage savings has come up a lot. And also our O&M costs have come up a lot because we're charging and discharging that battery much more frequently. So we have to now account for that in the overall savings that we achieve. When we switch to DR enrollment, this bottom strategy, all of a sudden everything changes. Those DR events are the majority of the savings. Notice that the demand savings are still the most important with peak clipping, second most important, but the most important is ultimately the DR savings. And kind of similar in the load shifting strategy, DR savings are substantial, but now usage savings actually become quite significant, and demand savings not as much, in part because the DR event actually takes care of a lot of those savings anyways. So let's look at this as a breakdown over a couple of years for this one particular client. Okay, so you'll notice what we're doing in this graph is we're plotting ultimately that initial capital cost. So you can see this particular battery is going to cost them around $4 million, a little over, to install. And then ultimately we're going to be regaining some of that, and it's basically a cash flow diagram. And we can see that we become profitable with this battery storage installation for this particular case sometime between about 2.5 and 3.5 years. And you'll notice it's kind of funny. There's this general upward trend, right? We have a very slight increase there, but then we have all these steps. You know what these steps are? Those are our demand response events, right? So right around the 6th month, right around June, they kick in. So we have a couple of demand response events here. Those are those big savings, and we see them year over year. That's really the reason why this is ultimately becoming profitable so quickly, because of the demand response savings. We ultimately plotted this for different utility rate increases, and as you can see, utility rate increase doesn't make a huge difference. I mean, yeah, we're talking about 2.7 years to about 3.5 years difference in terms of when it pays back, but overall, not a huge difference over a decent range of utility rates. Same thing for inflation. We see a little bit of a spread between about 2.8 years and about 3.8 years, but ultimately inflation rates don't drastically change the feasibility of battery energy storage. And then we also ran this for O&M rate increases, and as you can tell, O&M rate increases basically have very little to do with the economics of the system. It's really driven by demand response events, and then either demand savings or usage savings, depending upon how you carry out the control system for the battery. So now getting to the point that we were trying to get to from the beginning, can we do this not only for price, but can we do this for carbon? In order to do this, we need to maximize, again, those savings, but we need to do it by giving carbon a cost. We do that by building in this additional term into the optimization, but we now need to fix a price to that in order to put it on the same level for the optimization, okay? So we're going to give it a price based on something called the social cost of carbon, which you're probably familiar with, which its estimated range anywhere from $11 to $212 per ton of carbon reduced. Ultimately, we're going to use a value of about $51 per ton, just to give us a sense. That's a current administration's point for it, and that's obviously very variable, makes a big difference, but let's just use that as a starting point for us to get a sense of what our model can do and how we can ultimately reduce carbon emissions by building this in. I now want to compare for you. We've seen a lot of these graphs, just a few more. Stay with me. What you're seeing now is we're enrolled in demand response. We do have load shifting strategy, because we've seen, and what I'll show you later is that that's really the better strategy in general for the economic feasibility. But the only difference between these two is whether I'm optimizing for just cost. So this right one, I'm just optimizing for cost, whereas this left one, we're optimizing for cost and carbon dioxide reduction from the grid. Okay. Notice pretty similar, right? Ultimately, same initial profile. We see that at the beginning of the day, we charge in both cases, but this one stops when we account for carbon and then charges a little bit more and ultimately stops charging between about 7 a.m. and about noon, whereas this one maximizes, or at least does quite a bit of its charging between 9 a.m. and noon, okay? And then ultimately discharges everything quickly, whereas this one holds that charge longer before it discharges. How do we explain these differences? The only difference is how we're optimizing it, but overall, same time of use pricing, same other factors built into the model. The difference is what we call these marginal emission factors. And as I mentioned before, you can get these for pretty much any state and just kind of see how the grid intensity for either carbon dioxide, NOx, or SOx changes hour by hour. So what you're seeing here is that these are the marginal emission factors. The data is only available hourly, which is would be nice if we had it a little bit more frequent, but that's what we have. You can see that right here around midnight, that's when we have the lowest carbon intensity for this particular day. So of course the battery takes advantage of that by charging. Then we hit this point where we're a little bit higher in terms of our emissions. So we're going to not do anything there. And then we hit kind of a low point in the middle of the day. We're going to fully charge at that point and make sure we're fully charged before the time of use pricing goes up. Then we're going to hold on through this period when we've got high emission factors from the grid. And then ultimately, this is the point where we start hitting high time of use pricing. We're going to discharge through all of that. Okay. So now that we've optimized for not only cost, but the thought that CO2 emissions are important as well, we've now built a profile that tries to avoid those times of day when we're hitting high emissions from the grid. Looking at the cost optimization alone, what's kind of interesting here, and it's probably no surprise to any of us, we charged a lot even when the rate went up. We didn't do anything when ultimately we had really low emissions, and then we charged again when we had high emissions, and then we discharged everything right away. And ultimately, you'll see that by shifting out a little bit to the right, we avoided some of these high emissions at the late part of the evening. Right? So we took advantage of all of that by optimizing for both. With that built in, let's look at the scenarios and how this works out for a bunch of clients. Getting a little bit of feedback there, if anyone could mute, if that's all right. What you can see here is 10 different clients, 5 industrial, 5 commercial. And what we're looking at is discounted payback period. You'll see that the peak clipping strategy is not very economical in terms of discounted payback, about 50 to 70 years for many of these clients. Whereas load shifting with DR, we're really hitting pretty good paybacks, around 10 years for most of these clients. Okay. What's even more interesting, though, is that we can actually save significant carbon dioxide, right? Between around 0.1% or less with the peak clipping strategy, up to in the ballpark of 10% or more when we go to load shifting across these clients. Now, this is still pretty early because we've only run like really one scenario to try to understand how much carbon we can really reduce. This is scope 2 emissions of carbon right from the grid. Ultimately, though, we're optimizing this for a range of scenarios to try and understand, when the demand response pricing goes down and then CO2 savings become more important, how much can we really maximize? We're thinking about how much, what are the trade-offs between the cost of carbon and other potential savings that allow us to maximize it, and what should those prices be if we really want to see both really high savings from the for the clients and also really high CO2 savings from the grid as well. How do we co-optimize both, and what are the right points and price points to be able to hit and optimize both of those together? Those are some of the things we're working on right now, and I'll tell you how we're doing that. This is really getting into some of the future work. We've been able to get data for about just under 1,000 clients now, representing a range of commercial and industrial facilities. What I've plotted here for you is just their different NAICS codes, just the first 2 digits, so you can kind of see what types of facilities we're talking about. We do a lot of work with industrial facilities, so we have quite a few here in the manufacturing space that we're interested in, and we'll be optimizing across, but we've got a lot more data for all of them. What we're ultimately doing is we're running this optimization code through all of these clients to understand bigger picture trends that you can't see when you only look at 1, 2, or 3 facilities. And these are just some really preliminary results that were just coming out recently. We've optimized for different control strategies, discharge time, so that's the amount of time the battery discharges for. You have a lot of choice there. Ultimately, we've optimized it across a large range of energy storage size and demand response benefits, and we're also going to be adding to this the CO2 savings. One thing I'll note is that almost every one of these clients optimizes for load shifting. And there's about 7 or so that optimize for peak clipping strategy, but ultimately, even when they optimize for peak clipping strategy, the load shifting strategy is only about a month or 2 difference in terms of the payback period. So generally, the most economic opportunity for them is to load shift. And you can see that's true for almost all these clients across a large range of average facility demands. We also see that these actually can be really competitive. So you can't maybe get a good sense of the scale here because there's a large range, but some of these clients get down to about 4 or 5 year payback times at the minimum. A number of them optimizing around the 5 to 10 year range. So actually, this is really cost competitive, especially if you can take advantage of demand response benefits for these clients. So with that, I'll try to wrap up here by saying that we've looked at a number of control strategies. There's what we call load shifting and peak clipping. Generally, we found that load shifting, even though there's a lot of discussion about peak clipping, it's really generally not economical from what we found by looking at real data for a bunch of clients. It's really the load shifting, that daily shifting of the energy use profile that really maximizes demand. And that's not probably too surprising for those of you who work with on-site generation. We generally know that if you install it, you use it more. You don't install a CHP system to run once a year, right? And that's pretty true here as well. We want to use it frequently. Okay, another general thing we found is that demand response events are critical. And the pricing and the savings for them is so large that it really drastically changes the feasibility of battery energy storage, bringing it down into the 5 to 10 year range for most clients. And that's, based on some pricing from the last year or two. As I told you in the beginning, that pricing keeps coming down. And so we're going to see a further reduction in that payback period as we go forward. We're also see that we can actually reduce scope 2 carbon emissions. We've got a lot more work to do in this space. So I'm just kind of showed you some of the early results, but we do believe that we can see pretty significant scope 2 savings just by thinking about when to charge and when to discharge the battery. And ultimately, we'll be able to make a lot more conclusions once we've looked across a really large set of facilities to understand what the big picture trends are, and hopefully to understand what is it about those facilities and their energy usage profiles that makes them really good candidates for these strategies. So with that, I'd really like to thank you for your attention, and look forward to taking any questions.
Okay, thank you very much. Thank you. Okay, any questions? You have one coming. Okay, but Dr. Lee, this is not a question, right? It's a comment, the chat. Okay, so the question is, what are the potential big C emission reductions?
What are the potential emission reductions of carbon dioxide? Yeah, so that's what we're looking at right here. So you can see we anticipate anywhere from less than 1% up to maybe as high as 10 to 20% for some facilities. Not insignificant, and we're still optimizing this across that really large data set. We've recently updated our optimization just a little bit to try and make it hone in on these savings even better than it was before. And so these are built with that old optimization code. You can read more about this in this prior publication, but we're now looking to see if we can achieve even higher savings by the way we've optimized this now. And so preliminary, but is anywhere in that range of less than 1% to maybe on the order of 10 or more percent CO2 reduction just by leveraging that change in the marginal emission factors. Hopefully that answers the question. If I missed it, let me know. We did not optimize for NOx or SOx, but you could do that as well with the same general strategy.
Thank you. There is another question here in solving the In solving the optimization problem, did you happen to use any kind of deep reinforcement learning technique?
No, we've not done that yet. So initially there was that's something that we've been talking about, is that there's definitely a need and an opportunity for, and so we're we're still in too early on, but we'd be certainly interested in discussing that with others who have some interest in that space, and ultimately to try and understand what makes some facilities good candidates and others not so good candidates. Oh yeah, that's a great question.
Okay, thank you. Another question here. Thank you for a great presentation. I was wondering, what is the discount rate that you used in your NPV analysis?
If I'm not mistaken, we used around, for a lot of these analyses, I think it was around 3%. So it definitely, that was something that you can vary quite a bit, although it makes a little bit of an impact, but I think we used right around 3%. I have to go back and double check if we've maintained that consistent across all of our studies.
Thank you. There is a follow-up question to question number 1. Are these facilities going to be able to participate in the greenhouse gas credit sales?
If you did this, could you try to use this? That's a great question. I don't know if we know the full answer to that. We know for sure that from an industry standpoint, they can use this as justification for trying to meet some of their carbon reduction goals. One of the challenges that a lot of people note with this kind of work, we're looking at historical data to try to say what's the potential, right? But ultimately, as you start to have a bunch of these systems, they're going to start to shift how the entire grid operates. And so in the long run, we're going to need a system where you can know instantaneously how that's changing, because you're not going to be able to look back at historical data. So I suspect there's going to be some challenges in terms of having that as justification, but I think a company can certainly look and say, well, by charging and discharging here, they will be able to quantify carbon emissions reductions from the grid and potentially take advantage of those savings.
Thank you. How do you discharge, or how do discharge?
In terms of the model, the model's constrained so that it can't discharge faster than its maximum discharge rate, okay, which is also related to its maximum charge rate. They're usually pretty similar. And generally, the model decides to charge and discharge based on pricing. The price points are the main drivers here. And so whether it's trying to capture usage savings, demand savings, or as we saw at the later end, trying to capture carbon reduction savings, that's ultimately how it decides when to charge and discharge at one time versus another.
Okay, I think there's Laura's typing question now. Yeah, thank you for presentation, very helpful. So that's not a question, it's a comment. Now, question is, how do regulations affect the deployment and operation of battery energy storage systems?
Yeah, so there's definitely some discussion on this. We were in a conversation recently about battery energy storage, and it turns out that if you enroll, depending upon how you get, if you get, like, for example, an incentive from the grid or the government to install a battery, in some cases they will not allow you to sell back that energy to the grid at any point. So that makes a big impact. So I showed you one scenario here where we, for example, under the demand response scenarios, we actually want to be a net exporter with that battery system at certain times of the day, during the demand response event in particular. Well, some regulations do not allow for that. It depends on, if you've gotten certain incentives to install the battery and so forth. And we're seeing, we've seen drastic changes, right, in solar in this space, where it used to be a lot of discussion around net metering. Well, now it's discussion around net billing. We shared some of these results with the utility company, and they said, wow, we may not want to incentivize battery installations for demand response. This makes too much sense for the clients and maybe not as much for us. So we're still kind of at the early stages, because you're seeing this rapid growth in the use of this technology, but I suspect as more comes out, that will certainly make an impact.
Okay, thank you. I don't see any other questions, but I see comments saying thank you very much for the presentation and for your time.
Well, really appreciate the chance to share this with you. We've got a lot more data coming, and we're recently started doing work with solar plus battery installations for all these clients as well. And we've got a lot to learn, but we appreciate the interest from all those in the field.
Thank you very much. And yeah, this will conclude our webinar for today. Again, thank you very much for your time and for the very interesting and valuable information. Thank you.
Thank you.